In this video, we will talk about conservation of linear momentum in inelastic collisions. In particular, we will see how conservation of momentum is applied to inelastic collisions, both for one-dimensional and two-dimensional cases. Finally, we will solve some problems to better understand the concepts provided. Let's first start by defining what an inelastic collision is. Inelastic collision is a type of collision in which linear momentum is conserved. So we write the initial momentum is the same as the final momentum. That is to say, the momentum before the collision is the same as the momentum after the collision. The second condition is the kinetic energy is not conserved. So the kinetic energy before the collision, that is, the initial kinetic energy, is always greater than the kinetic energy after the collision, or the final kinetic energy of the system, signifying a loss in kinetic energy of the system during the collision. The following diagram depicts what happens in a typical one-dimensional collision. The top diagram shows two objects, mass 1 and mass 2, approaching each other with velocity v1b and v2b respectively. After colliding, m2 moves to the right and m1 moves to the left. m2 moves with velocity v2a and m1 moves to the left with velocity v1a. Another scenario is when two blocks, mass 1 and mass 2, initially moving along the same direction with, of course, v1b greater than v2b. And then they collide, and they may be moving in an opposite direction after the collision, or both moving in the same direction to the right after the collision, depending on how large this v1b is compared to v2b. So these are just different possibilities that may occur. Another possibility is when the two masses collide and they stick together and they move as one system after the collision. Such a collision is known as completely inelastic collision. Inelastic collision can also occur in two dimensions, in which both mass m1 and m2, they now move on an xy plane, for example. So there is angles theta 1 and theta 2 that need to be taken into account when applying the law of conservation of momentum to collisions in two dimensions. And since momentum is a vector, both the x component and the y component of the momentum of the system are conserved separately, as given by this equation, which implies that the x and the y component of the momentum of the system are conserved separately. Now, the subscripts b and a refer to before and after the collision, respectively. Let's look at the following problem. Two masses, A and B, they move towards each other on an air track with a speed of 3 meters per second as shown. After they collide, B moves away with a speed of 3 meters per second. What is the final speed of A? So let's first calculate the initial momentum of the system. So the initial momentum of the system consists of initial momentum of object A, which is 0.5, that is the mass, times the velocity, which is 3I hat, it's moving to the right, and the momentum of object B is the mass, which is 0.4, and the velocity is minus 3I hat because it's moving to the left, and that is 0.3I hat kg meter per second. The momentum final, or after the collision, will be the momentum of object A, again 0.5, that is the mass of object A. Now we don't know what the velocity of A after the collision, that's exactly what we want to find. For object B, the mass is again 0.4, now it's moving 3 meters per second to the right, so the velocity is 3I hat. Due to conservation of momentum, we will equate the final momentum to the initial momentum being 0.3 I hat. So by equating this line to 0.3 I, we can solve for VA, which is the final velocity of A, and we will get minus 1.8 I hat meter per second. So that means VA will be moving to the left with a speed of 1.8 meter per second. And that solves the problem. Now we can also check that the initial kinetic energy, when calculated, will give you 4.05 joules, and the final kinetic energy is 2.61 joules. So it fulfills the condition of inelastic collision, because the final kinetic energy is indeed less than the initial kinetic energy, indicating a loss in kinetic energy during the collision. Problem 2. 2 chunks of ice sliding on a frozen pond. The surface is frictionless, so chunk A with mass 4 kilograms moves initially with a velocity of 2 I hat meter per second, that is to the right. It collides with chunk B with mass 3 kg, which is initially at rest, so that one is at rest. Now after collision, A moves with a velocity of 1 meter per second, right there, along an angle of 35 degrees above the line of initial direction. So the line of initial direction is to the right along the x-axis. What is the velocity of B after the collision? So let's first write down the initial momentum of the system before the collision, that is. So the momentum is only due to object A, so the mass of object A is 4 kg, and the velocity is 2I hat. B is not moving, so the initial momentum of the system is quite simply 8 I hat kg meter per second. Now let's do the final momentum of the system. The final momentum of the system is the final momentum of object A plus the final momentum of object B. So let's calculate the final momentum of object A. Now A is moving with 1 meter per second at such an angle, so its mass is 4 kilograms. The velocity is 1 times cosine 35 degrees, so that is the x component of the velocity, and the y component of the velocity is 1 times sine 35 degrees, j hat. So that is the momentum, the final momentum of object A. The final momentum of object B. Well, we don't know its velocity, but we do know its mass. The mass is 3 kilograms, so it's just 3 times VBF. So VBF is what we are looking for. So adding this and that, we will get the following for the final momentum of the system. So that is the final momentum of the system. Now we have to equate that to that, and we can figure out the only unknown, which is the final velocity of object B, which will turn out to be 1.574 I hat minus 0.765 j hat meter per second. The magnitude of that velocity can be determined in a usual way, like how we computed the magnitude of any vectors. So minus 0.765 squared, and that will be 1.75 meter per second. So that is the magnitude of the final velocity of object B. Now what about the direction, meaning this angle here? Let's call it beta. Now because the x component is 1.574 and the y component is minus, you can ignore the minus, 0.765 because we want to compute this acute angle beta. So tangent beta is 0.765 over 1.574, and that will give you 26 degrees for beta, and that is the direction of the final velocity of v, and that solves the problem. Problem 3. A 5-gram bullet is fired horizontally into a 2 kg wooden block. Initially at rest, that's this one, on a horizontal surface. The coefficient of kinetic friction between the block and the surface is 0.3. Now after the collision, the bullet remained embedded in the block as shown here. The block slides 0.2 meters along the surface before stopping. Find the initial speed of the bullet. So find VB. So the initial momentum of the system is simple. The initial momentum of the system is quite simply 0.005. That is the mass of the bullet times the initial velocity of the bullet. The wood is not moving, the block of wood is not moving, so it doesn't contribute to the initial momentum. So only the momentum of the bullet counts. Note that I have converted the gram into kilogram here. The final momentum of the system is the momentum of that block bullet system that is moving together and taking off with a speed Vf just before the friction starts to act. And that is the mass of the block plus the mass of the bullet in kg times that the common velocity of block bullet system. And the idea is to equate the momentum before and after the system. But since we want to find this, but we don't know this, we need to figure out what this is first. So how do we find the final velocity of that block bullet system as it takes off? Note that as the system takes off with speed Vf, and then it comes to a complete stop after traveling 0.2 meters. So we can use the work kinetic energy theorem to get the takeoff speed of that block bullet system. So what is the work? Work is done by friction. So that is given by this expression right here. Mu k times the normal force times 0.2 meters. And the right hand side is the change in kinetic energy. The final kinetic energy is 0, so that is 0. And the takeoff kinetic energy is half times mass times this takeoff speed squared. Now we know what mu k is. Mu k is 0.3. Normal force is the weight, mg. The distance is 0.2. And the work is negative because the displacement is to the right, friction is to the left. And the right hand side is, so the work is negative. The right hand side is minus half times mass times the takeoff speed squared. So the mass cancels and you can find the takeoff speed. And the takeoff speed will turn out to be 1.085 meter per second. Substituting this result in the conservation of momentum, we can solve for the initial speed of the bullet. So let's equate the momentum, initial and after. So final momentum is 2.005. This final speed is 1.085 equals, initial momentum is 0.005, that's the mass of the bullet, times the speed of the bullet. Now both the Vf and Vb are moving to the right, so we have dropped the I hat from the calculation because at this point it does not matter. And we can solve for Vb. And when we solve for Vb, we get Vb to be 435 meter per second. So that is the initial speed of the bullet. And that solves the problem. Thank you for watching.